In this video, we introduce LossLens, a visual analytics framework for diagnosing deep learning models from a loss landscape perspective. The framework has two major components, global analysis and local analysis. Global analysis shows the global structure of loss landscapes for models of interest. Local analysis provides a comprehensive visualization of the local structure of loss landscapes for selected models, including a loss contour view, persistence diagram, and merge tree. Our first case study illustrates how our framework can be used to investigate models with different architectures. The goal of this case study is to diagnose whether residual connections in ResNet 20 can cause significant changes in terms of the loss landscape. The analyst trained 4 models separately for ResNet 20 with and without residual connections. From the global structure view, the layouts appear similar in that both of them do not show an obvious pattern. This observation suggests that the models may not have an obvious global organization in high-dimensional space. First, the analysts noticed that although the average performance of the two models is similar with an accuracy around 90 to 92%, the mode connectivity between ResNet 20 models with residual connections is better than the mode connectivity between ResNet 20 models without residual connections. This is indicated by thinner and more curved lines connecting the different models. The analysts wonder if removing the residual connections can significantly affect the loss landscape smoothness, matching the intuition suggested by prior work. In terms of CK similarity, the analysts noticed that the structure seems similar in that neither model has an obvious pattern or spatial organization. This similarity, encoded by the distance between circles in the two-dimensional graph representation, suggests that both models make similar predictions, which could be explained in part by the fact that both models were trained on the same data. The observations made based on the global structure views indicate that ResNet 20 with residual connections has a locally flat, globally well-connected loss landscape, and that some trained models are similar. In contrast, ResNet 20 without residual connections has a locally flat, globally poorly connected landscape. It is noteworthy that for ResNet 20 without residual connections, models 1, 2, 3, and 0 are very close to each other, yet their connectivity is relatively poor. This was not observed for ResNet 20 with residual connections, which suggests that higher barriers are directly related to the removal of the residual connection. Next, the analysts explore and compare the local structure of model 2023 for ResNet 20 with and without residual connections. They notice that ResNet 20 with residual connections has a flat loss landscape compared to ResNet 20 without residual connections. This is confirmed by the persistence diagram view, where ResNet 20 without residual connections displays larger fluctuations compared to ResNet 20 with residual connections. The merge tree for ResNet 20 without residual connections also shows many saddle points and local minima, whereas the merge tree for ResNet 20 with residual connections shows only one minimum. This suggests that residual connections in the ResNet 20 architecture result in a better loss landscape both globally and locally. This case study shows that even though the performance differences between models with and without residual connections is small, we can still see significant differences in the structure of their loss landscapes. In our second case study, we show how our framework can be used to diagnose and analyze models where constraints are applied to the loss function during training. Specifically, we look at physics-informed neural networks, also known as PINs. The goal of this study is to investigate the soft regularization used by PINs by seeing how the loss landscape and prediction error changes as a physical parameter is varied. Here we look at PINs trained to solve simple convection problems, and we vary beta, a physical parameter corresponding to wave speed. At first glance, the analysts noticed that the models trained with beta equal to 1 are closer to each other than those trained with beta equal to 50. After filtering out high mode connectivity edges, we still see many curved lines connecting the models trained with beta equal to 50, indicating that the higher value of beta results in more poorly connected minima. To verify this hypothesis, the analysts select 2 models with different values of beta for further local structure inspection. After filtering the mode connectivity value using the slider in the Global View setting panel, the analysts select models 41 and 90, since the former is well connected to other models and the latter is poorly connected to other models. It turns out that the loss landscapes of the two models have many differences. The one trained with lower beta has a flat loss landscape, and the one trained with beta equal to 50 does not have a very clear minimum. However, the persistence diagram shows that the terrain of the model trained with beta equal to 50 is very rough and complex around the minimum. It is also apparent from the merge tree that there are many more branches for the model trained with beta equal to 50 compared to the model trained with beta equal to 1. Together, these insights suggest that increasing beta can lead to a poorly connected, locally sharp loss landscape, thereby making the PIN model more prone to failure.